Aloha, everybody. We're waiting for one more person to be let into the room. Okay. Aloha, everybody, and thank you for joining us for September's third Thursday. Today's topic is forecasting the evolution and stability of Sierra Negra Volcano, Galapagos. Our featured presenter is Dr. Trish Gregg, professor and associate head of the Department of Earth Science and Environmental Change at the University of Illinois, Urbana-Champaign. Before we begin, I kindly ask that you place any questions or comments in the chat. We'll read them at the end of the presentation. And any resources posted in the chat will be shared to you after via email. So without further ado, I give it to Trish. Trish, thank you so much for joining us today.
Thank you so much, Amy, and thank you so much for inviting me to join your webinar today. I really appreciate it. I've had a lot of fun going back to look at some of the older webinars and learn a lot about disaster preparedness that I think it's such a great resource to have all of these webinars available. Today is a little bit different than some of the previous webinars in that it's more focused on the science side of how we're thinking about forecasting and what we're working on in volcanology to provide information to mitigate risk and hazards for those that live on or near volcanoes, or even those who are flying over volcanoes, maybe if you're talking about the illusions. I'm a geophysicist, geodynamicist, and a lot of work that I do is to better understand how we can create models of volcanic systems so that we can better understand why and how they erupt. Before I jump into it, though, I do want to quickly thank all of my collaborators and my amazing students and team here at the University of Illinois. One of the reasons I love my work so much is that I get to work with such incredible young scientists as well as amazing colleagues around the world. So I do want to give a shout out to them. Many of them have been very instrumental in this work. In particular, Jack Albright and Yan Shan, former students, have both been very important in the development of the techniques that we're going to be talking about today. So a little bit of where we're going to go. So a roadmap of what we're going to talk about today. So first, I'm going to talk a little bit about why we're doing what we're doing to better understand how to forecast volcanic eruptions and sort of the motivation for this work. Then I'll go into the approach a bit. It's a little bit on the mathy physics side, but I'll try to keep it as brief as possible because the really exciting part then is our work in the Galapagos and the forecast that we used for the 2018 eruption of Sierra Negra Volcano. And then I'll wrap up with some conclusions and future work. And I am very excited for discussion at the end of this talk to hear your thoughts as well and ways that we can enhance what we're doing to make our science accessible and useful to monitors and those who are helping people prepare for volcanic eruptions. So in terms of motivation, the in the field of volcanology, the national academies put out the Erupt report and in 2017 and outlined some of the grand challenges in the field of volcanology, the things that volcano scientists around the world should really focus on here as we move into these next decades. And one of the things that they pointed out was this understanding and documenting the repose, unrest, and precursors and timing of eruptions during the entire life cycle of a volcano. And this part, the second grand challenge, is part where I really have spent a lot of time in my research. And that is developing quantitative models for the processes that govern volcanic eruption and using these to forecast the size, duration, and hazard of eruptions. Off to the side here, I have this map that was in the National Academy's report. It's showing the active volcanoes in the United States, Canada, and northern Mexico. And something that I like to show, especially when I'm giving these types of presentations to a broader audience, just as a reminder that the United States hosts a lot of active systems, and that can impact a lot of people, not only those who in those communities that live on or near volcanoes, but also, as I mentioned, those who may be traveling across the United States, maybe in a circumpolar air route that would fly over, for example, the Aleutian arc of Alaska. So understanding these volcanic systems, being able to provide forecasts of them is really important, not only for those on land, but perhaps those who are traveling in the airspaces above. So one of the big challenges and one of the big goals of my group is taking the amazing data sets that we have for monitoring volcanic systems and combining them with sophisticated numerical models. So I have this image here that was from a paper that I wrote with Matt Pritchard, who's a professor at Cornell, which is a large integrated study that was conducted on Ururuncu volcano, located in Bolivia. It's right here on the edge of Bolivia, Chile, and Argentina. And this was a big study that used magnetotellurics, GPS, gravity, SAR satellite information, as well as seismometers to better understand this volcano and its evolution. And when you see these types of volcanic systems, this is becoming very common where we have these large, amazing data sets, but they have gaps in those data. There may be gaps in the timing of when the data is collected. And even though it's giving us direct coverage, there are many questions that we still need to be able to address to cover those data gaps. And then, so on the other side, what we have is our models of the physical system that may give us some great information about how the system evolves, but oftentimes we create these models, we know they're imperfect, and we don't necessarily have a great grasp on what the errors in our models are. So the concept of model data fusion is taking these incredible data sets to both improve our models, but then also using the models to improve our data. So the idea being that the data improves the model's performance by allowing us to adjust unknown parameters or variables in our model and correcting our model trajectory. And then our model can be used to help tell us where to target new data and constraining the gaps in our observations. So the goal then is a situation where you have a physics-based model that's producing forecasts of a volcanic system, or any system for that matter, and then you have observational inputs that are correcting that model, and then there's that feedback loop where our model's telling us where we need more data, our data is coming back and improving our model, and then our model, ultimately, the hope is that it can provide forecasts to tell us the timing and location of potential volcanic eruptions. So one of the things that I've spent the last decade plus working on is how do we develop these models? What do these models look like? And what kinds of models are most useful, especially for volcanic systems? For the most part, I find finite element analysis and finite element models to be very useful in these types of scenarios because they provide information about the stress and the strain of the system as it evolves. So in particular, I've been using COMSOL multiphysics, which is a finite element modeling software that provides a way to combine lots of different physics into the modeling framework. And today I'm going to be showing models using an elastic model for a volcanic system. And this is what it looks like. Basically, you have a box with rheological information such as temperature and the various elastic moduli, density, they're gravitationally loaded, and then there's a temperature structure that's applied to the edges of the model that gives you the geothermal gradient, and then there's a magma chamber embedded in it. And then we can mesh this model, and this magma chamber, then we can allow it to expand and grow as new material is entering into the model system. And what's really quite useful about these models is this relationship between stress and strain. And so stress being the stress of that magma chamber as it is expanding, and strain just being the deformation that's created. So as that magma chamber is growing, it's going to push up the land surface. We'll be able to view that through GPS or INSAR data, looking down at the volcanic system, and then we can sort of back calculate, well, what's the stress of the system look like? And the stress of that system is going to then tell us where there could be potential for eruption. And we can also do things like adding heat to the system. We know that magmatic systems are hot, and there's a lot of things that happen rheologically to the rocks when you heat them up, and that becomes really important. So all of these models, though, are very well benchmarked. We are very careful about taking any sophistication, any updates to our models and benchmarking them with analytical solutions and other numerical solutions to make sure that the model is doing what we think it should be doing and it makes sense for the physics that are involved. Now, as I mentioned, that temperature can play a really big role. And in this image here, I'm showing the Young's modulus, which is the elastic moduli that controls that relationship between stress and strain and temperature. And these are a bunch of rock deformation experiments that were conducted at the University College London's Rock Laboratory by Smith et al. And these are uniaxial experiments, and it's showing that the Young's modulus, as you heat up the rock, decreases quite a bit. And this becomes really important when we're thinking about a magmatic system, especially a long-lived one that might have a lot of heat coming into the system, because as we heat it up, your material properties around the magma chamber are going to vary. And so if we're thinking about, well, when is the magma chamber going to rupture and initiate a dike that could create an eruption, you need to know something about the material properties. So what I'm showing here is a temperature structure, a thermal structure. The magma chamber is located here in the middle, and it's just showing that near the magma chamber it's warm, away from the magma chamber it's cooler, and then you also see that temperature gradient from having the geothermal gradient applied into the model. And then below here is showing how that impacts the Young's modulus. So you can see that the Young's modulus is quite low near the magma chamber. So all of these things play a pretty big role, especially when we're trying to model failure in the system. But one of the big questions, and something that I grapple a lot with in my group, is how do we quantify failure? In fact, I have a very talented PhD student, Lexi Dunn, who's working on this now, who's like in the laboratory squishing rocks at high temperature, trying to understand how they fail. And I'll say that there's not that much information. So one of the things that we've played around with in our modeling is how can we quantify failure, so when the rocks are going to fail, and what might that look like? And we've sort of come up with 3 different things that can quantify failure for a magmatic system. The first is more Coulomb failure. This is often called shear failure, and it's the type of failure that occurs that generates an earthquake. In this particular type of failure regime, you look at the normal stress and the shear stress, and you look at the largest normal stress and the smallest normal stress, and you compare those, create a circle, and then see if it intersects with the Coulomb failure plane. And this Coulomb failure plane is a function of the internal angle of friction of the rocks and the cohesion of the rocks. So when failure occurs, shear failure, when it hits the more Coulomb failure plane, it usually will generate an earthquake. So in our models, we can actually use this to compare to seismicity to see, are earthquakes being induced due to the expansion of the magma chamber. The other type of failure we can look at is tensile failure. Now, tensile failure is something that intuitively is something that will be more important for a magmatic system. So tensile failure is opening failure. So it's when you open up a crack. And that's what we'd expect to happen along a magma chamber boundary. It will open up, and then you'll have magma that will exit the system through that opening. So one of the things we can also check in our model is, are there areas within the model space where tensile failure is occurring, where you see tension in the model space that could allow magma to propagate? Finally, there's sort of this term that we like to use a lot in volcanology called overpressure. And you probably have heard this if you've listened to somebody talking about, oh, a volcano was erupted because the magma chamber overpressurized. It got so much pressure that it couldn't hold in the magma anymore, and that pressure caused the eruption to occur. Overpressure is a really tricky term, because when we're thinking about a magma chamber, even though I'm describing it as like a hole filled with magma that's expanding, we know that's not really the case. Magma is probably in sheets or sills that interact with each other rather than like a holding tank. So as things overpressurize, it probably doesn't look just like a big chamber that's expanding and then suddenly the pressure's too much and it explodes out. but it still is a useful thing to calculate and look at. And there have been previous studies that suggest that there are certain overpressures that appear to coincide with when a magma chamber or a magma chamber may rupture and a volcano might erupt. So we do track that in all of our models just to see what it's doing. But just as sort of a spoiler for the talk, we do find that these Coulomb failure and tensile failure seem to be governing the timing of eruptions a little bit more in the case of Sierra Negra. So I mentioned about data assimilation, and this is the crux of how we take all this information and pack it into our models. We're using something called an ensemble common filter. And this may sound really fancy and a little bit uh, sophisticated, but I want to say this is a technique that's been around for a while. It's something that's used to track hurricanes and weather patterns. When I was a postdoc at Oregon State, I went to this incredible PhD defense where Greg Wilson, who's now a faculty member at Oregon State, showed how you can use this technique to track rip currents for surfing. And I saw that talk and thought, wow, that's so cool how you do that. So he was looking at data coming off of the surf and using the images of where white caps were breaking coming into the shoreline to update his models of bathymetry and then update models of rip currents off the coast of Oregon. So we're doing a very similar thing for volcanology. We're taking snapshots of what the volcano is doing at the surface and inverting it to understand what's happening at the magma chamber level. It's called an ensemble approach because we run hundreds of models at the same time. And you've probably seen this maybe, but not had thought about it when you're looking at hurricane forecasts, and you'll see that cone of probability, right? You see the map of the land and you'll see a hurricane coming towards land and there's that cone of probability. So near the hurricane, we kind of know where it is and we know the path it's going to take. And as it gets closer to shore, that uncertainty gets bigger. Well, it's the same thing. It's using an ensemble approach where you're running hundreds of models, and as those models get further away from where you are right now, that cone of probability expands because the models sort of go off in their various directions. So we take an ensemble of hundreds of volcanic models and we combine them with the measurements. In our case, we're using geodetic measurements such as GPS and INSAR, so the deformation of the land surface. And then we combine them in what is called the ENKF analysis. And the ENKF analysis is actually a fairly straightforward analysis where you take your forecast of the model state, and this is basically taking, down below shows you the forecast error and the measurement error. So how much I trust my model, how much I trust my data, and then seeing how close my forecast is to the current measurements. And then once that's done, you update to a new model state and run it again. So you project it forward in time. So every time I have new information for my model, I can update my model and I can send out a new forecast. So very similar to what is done in weather forecasting. So here, what we've done is we take this and put it onto a supercomputer. One of the things that my group has pioneered is using sophisticated finite element models to do this for volcanoes. So we were the first group that took this technology that had been developed for weather forecasting and physical oceanography and using it to forecast and better understand the evolution of volcanic systems. To do this, though, it does take supercomputing resources because these three-dimensional models where we're calculating stress and strain and we're calculating temperature, we're calculating failure, they do actually take a lot of computational effort. So we have taken this model and, like I mentioned, you're running hundreds at a time. You can send them off each to a different CPU, so running them all in parallel. The models that I showed today, I'll talk a little bit about how long they took to run, but they do actually take quite a bit of running time. And that's one of the things we're working on now to try to get around for future efforts. So now we're moving on to the Galapagos. Working in the Galapagos has been really incredible, and the team of scientists that are working on the volcanic systems there is just incredible. My particular group of scientists that we've been collaborating with since the mid 2000s, 2010 timeframe, are in Germany, the UK, Ireland, Ecuador. It's a really dynamic and large group of people. So I want to just orient us all to the Galapagos Islands. Up here to the north, you can see the Galapagos Spreading Center, and the Galapagos Islands are located to the south there, formed by the Galapagos Hotspot. The active volcanic systems are located here on Isabella Island and on Fernandina. The volcano that we're going to be talking about today is Sierra Negra, and it's the largest of the
It looks like Trish has paused. We'll give her a second to reconnect. During this time, while we wait for Trish to reconnect, if you have any questions, please put it in the chat. Oh, we lost Trish. I'm sure she'll be right back. I know there was a couple power outage today on the islands of Hawaii, so I thought maybe she'd be safe in Illinois, but maybe she's succumbed to the same fate. During the meantime, I see we have our executive director on, Dr. Carl Kim. Dr. Carl Kim, is there anything you'd like to say or any announcements you have?
Thank you very much for organizing this session. Yeah, I think it's a very interesting topic. I am particularly happy to see the connections between the weather forecasting models and the volcano models as well too. I know it's a very busy time right now, and I hope that we can continue to connect on these important topics as well. So hopefully we'll get her back.
Trish. Trish,
Hi, I'm so sorry. I don't know what happened.
all good, Trish.
I was just thanking you I'm Carl Kim from the center, and I really appreciate your connections that you're making with weather forecasting and
Oh,
storms as well too. And so that's great. Thank you very much for your presentation.
oh, you're welcome. I'm sorry I got kicked off for a moment. I'm not sure what happened, but I'm back. I don't know when I got kicked off though, so had we made it to
If
the
you
Galapagos?
want to go one slide previous. Yes.
Okay, so back to where we were. Apologies again. I didn't realize my internet was unstable. So for the study today, I'm talking about Sierra Negra Volcano. Sierra Negra Volcano is located here on Isabella Island. The active volcanic systems of the Galapagos are located on Isabella Island and Fernandina, and Sierra Negra is the largest of these active volcanic systems. The Nazca Plate in this region is moving due east at 51 millimeters a year. There are 7 young shield volcanoes, and these are overwhelmingly basaltic volcanoes. So the volcanoes in the Galapagos erupt a lot, and I like this image here that shows since 1960 there's been about an eruption every 2 years. So as a volcanologist, it's a really exciting region of the Earth to study because these volcanoes erupt quite frequently, giving us lots and lots of data. On this chart here, where I'm showing number of eruptions and years to present, you can see a couple of notable things here. You have 1831 when Charles Darwin arrives, and then 1959 when the research station is established. So it was after the establishment of this research station that we had observations on the ground that allowed us to record that these volcanoes were erupting so frequently. So this isn't that they weren't erupting, it just there weren't the observations there. So looking in a little bit more detail at Sierra Negra, you can see here's a map of the volcanic history of the eruptions of Sierra Negra. The major port town on Isabella is Villamil here, located on the flank of Sierra Negra Volcano. And you can see that there have been some eruptions that have made their way to the south. Most recently, though, in the blue and green colors are eruptions that have gone more towards the north. So one of the things we have been really interested in is why most of the eruptions have been heading northwards and whether or not there is risk and for those in Villamil of potential eruptions going towards the south. So using our particular modeling approach, we've been very interested in that as a possibility. So my first involvement with Sierra Negra was looking at the 2005 eruption of Sierra Negra. This is some vertical displacement data leading up to the 2005 eruption. So on this axis, you see vertical displacement, and here is time. For a while, there was only INSAR data available, so satellite data available for Sierra Negra, so telling us the inflation. And then in 2000, my colleague Denny Geist started to do GPS surveys, and they installed a continuous GPS array on Sierra Negra in 2002. It was very funny because right after they installed it, the volcano started to deflate a little bit. So they were very annoyed because it had been inflating, and then it sort of stopped as soon as they put the equipment out. But they didn't have to wait long because it immediately started to accelerate in its deformation and erupted in 2005. This is a photo of my colleague Denny. He and the team were at Sierra Negra during the eruption doing field work. So it was a very fortuitous situation where they were on the island collecting data and it erupted. So after the 2005 eruption, the volcano went back to sort of a background normal, but it still was inflating a bit. And I was working on other systems at the time, but in 2017, Denny and our Ecuadorian colleagues reached out to us and said, hey, we know you're working on this new forecasting framework and algorithm. Sierra Negra has been inflating a lot. Would this be something you would be able to look at? And at the time, I wasn't funded to work on Sierra Negra, but I had recently been awarded a fellowship at the National Center for Supercomputing Application. And this was a really nice target for us to focus on. So what I'm showing here is the line of sight INSAR observations for Sierra Negra at the end of 2017. And what you're looking at is the satellites looking directly down at the volcano. And this is how much it is expanding in meters per year. And then this is a look at it from the just from this point over time. So when we started looking at it, it was in 2017, and it had already started to really ramp up. And then as we moved through to 2017, we saw this big acceleration. So we took our 3D model and we adapted it for Sierra Negra. So again, this is the 3D model space. There's a magma chamber embedded in it. This magma chamber can move around in space. And one of the things that we're trying to do when we invert these models using data is we want to know where the magma chamber is in space and what the geometry of it is, because that can then tell us where magma might move if it were to rupture. So we have a number of parameters that we track, and then this is our ENKF implementation. So in this case, we use 240 models that we're running simultaneously. We iterate them 6 times. What that means is that before we go to the next time step, we let it assimilate information 6 times before we move forward. And part of that is with INSAR data, we only have a look at the volcano every couple of weeks. So there's a big time gap. And if we allow it to sit on that information for a bit, the model converges a little bit better. So the total time for our forecast was 680 hours on the computer, 1680 hours on the computer. One of the things I do like to point out is that to start the model, we have to give it sort of initial conditions for the models. And we tend to not want to constrain the model too much because we don't want to bias it from the start. So we tend to give it very large parameters. We say it could be in this space, it could be these sizes, and we're just going to let the data assimilation do the job of taking our observations and finding what that magma chamber should look like. So what this is showing here is that model in time. And you'll see when it starts, there's that big blip. And that's just all of the models at the beginning, all those 240 models. There's so many different parameter combinations that it's a huge space. But then it starts to collapse into a shape that matches the data really well. And so we're able to then track it through time. So at the end of 2017, going into 2018, we had run this model and we knew a couple things. One, that the magma chamber hadn't ruptured, there hadn't been an eruption. And for all of these models, we could do things like track whether there's reservoir tensile failure, whether there's shear failure. Again, the shear failure would be creating seismicity, and the tensile failure would be openings that could potentially initiate dikes. And we ran this model through January 27th, 2018. And this is what that failure looked like in our models on January 27th, 2018. And so what we had was some more coolant failure in red. So this would be areas where we would predict that some seismicity might occur. So we might get some earthquake nucleation. And then if there were going to be dike initiation, it would be in regions of tensile failure. Now, one of the things that was happening at this time, so I was doing this fellowship and I was invited to give a talk at the UNAVCO science meeting in, I believe it was April of that year, or March or April of that year. And so we took all this models and I took it to the science meeting and I presented a forecast for all of 2018. So I said, okay, as of January 27th, we know what this looks like, and we're going to run a forecast for the entire year and see what Sierra Negra might do. And this was sort of just a thought experiment. Like, can we actually track this volcano system through 2018 and say something about when the system might fail? So we did a 10-day rolling forecast for all of 2018 just by projecting these models forward into time. And we found in doing this that the model would predict through-going failure, or just it would not be stable at between June 25th and July 5th. And there were lots of caveats to this. We're using an elastic, homogeneous model, and we know that volcanoes are very heterogeneous. There are lots of faults. There are lots of things going on. We chose our failure criterion. We don't have this model particularly tuned for Sierra Negra, but having seen the previous eruption in 2005, we were able to say, okay, we think a failure criterion with a cohesion of 10 might work. And we assumed that the model, that the volcano would stay on the trajectory it was on. So this was the time that we chose. And the model chose, I shouldn't say we, the model chose this time, 940 days, which would be between June 25th and July 5th. And we gave this talk. And I didn't think about it again because we stopped looking at this model in January and I was moving on to other things. Well, Sierra Negra erupted on June 26th within that window. And my colleague Denny Geist called me up and he's like, Trish, Sierra Negra is erupting. What day did you say that it might erupt? And I was like, well, right now. And so we were kind of in shock. Like, how did this actually work? This shouldn't have worked. This was sort of just a thought experiment. But it turned out that not only did we do a good job of tracking the timing, like we also had a pretty decent understanding of where the rupture may occur. So this is the eruption map from that 2018 eruption. The first fissure opened on the north side of the caldera. Then you had fissures opening up here and here, and then the longest fissure, fissure number 4, that reached the ocean here. There was also a small fissure that opened off on the western side of the caldera, fissure 5. The other interesting thing about the eruption is that there was an earthquake that occurred just prior to the eruption, similar to what we saw in the 2005 eruption. So this is a look at the caldera rim. So you're sort of looking south along the caldera. So the caldera is here and the inner parts of the caldera here. And this is that fissure 1 opening up and the lava flows that were coming out on this 26th of June. So now that we had all this information, we of course wanted to go back and see what worked in our models and what parts of this can we learn from, because something obviously worked, even though I constantly say this was sort of a sheer dumb luck situation. Like the volcano just happened to do what we thought it might do, but it wasn't something that we were really prepared for having occur. So going back through the entire system, you can see here's the 2005 eruption, and we're looking at uplift in time. And you can see there are these little phases of eruptions. We know there was an intrusion in 2010, and then the volcano continued to inflate before the 2018 eruption. So we took all this information and we went back and we're like, okay, we want to run these models in a hindcast format. So forecast is where we're taking the model, running it forward in time. We don't know what's going to happen. Oftentimes we'll take data and run a hindcast. So basically, if we don't tell the model we know when it's going to erupt and we throw all this information in, will the model pull it back out? And so that's what we did for Sierra Negra. We took all the available data all the way up to the day of the eruption. And this is showing the data here, the INSAR data, the model calculations, and then the residual, showing that the model does a really good job of tracking that uplift and that we actually have very little error between our models and our data. And we did this for a variety of models. In the gray is our forecast that we started with, and then we ran 3 different hindcasts. And it's hard because for each of these, it takes weeks to run on the supercomputer. So it's like we'd love to run so many more of these, but we stuck to just 3 hindcasts. One hindcast assumed no temperature in the system. It's like, well, what if we assume Sierra Negra is cold? What would we get? One that was a temperature dependent model, but it only used one orbit from the satellite, so only ascending orbits, and then one that is a temperature dependent that used both ascending and descending orbits. So the green hindcast is our full hindcast that is all the information from everything. And you can see that all of these behave a little bit differently. So these are the parameters that we're tracking. Like I mentioned, we want to know where it is. So the XY location, the depth, we want to know the size of it. So these are the radii, the size of the magma chamber. We want to know whether it's rotating, strike, dip. So those are what these angles are showing. And then of course, here is our overpressure. One of the things that we found kind of fascinating through this process is how the overpressure varies amongst the models. And again, the overpressure really is a function of the size and the shape of the magma chamber, and it's a hard parameter to really nail down. And so what this is showing is the overpressure in time for all of the different model runs. Again, this green one is the one that has sort of the highest constraints of the model. And the gray here is the forecast. I put in this 10 megapascals because oftentimes people will say, well, 10 megapascals is enough pressure to erupt a volcano. But we're just, the overpressure just doesn't seem to do a good job. So the other things we track are these more Coulomb or shear failure and the tensile failure. Now, these are now just from that hindcast that had all of the information in it. And in retrospect, we also added a bunch of different failure criterions. So these C values are those cohesions for that failure envelope, showing how the different failure envelopes will impact the amount of models that are experiencing shear failure. This red bar here is when the eruption occurred. And then I put this red arrow in here because now after the fact, we can go back and look at the seismicity. And one thing that was really fascinating about Sierra Negra but prior to the 2018 eruption is that there was a sort of a background level of seismicity through 2016. And then 2018, there was this acceleration in seismicity at the volcano. And this red arrow here coincides with this red arrow here. And if we looked at a cohesion of 20, you can see this ramp up in shear failure leading into 2017. The other thing that's really fascinating is going into 2017, as the seismicity is ramping up, we also see a ramp up in the number of magma chambers that are experiencing tensile failure, which again would be needed to initiate a dike. And again, since we don't know what the tensile failure criteria is for this magma chamber, of course, we check a bunch, all the way from no tensile strength, which is this blue model, down to a tensile strength of 20 megapascals. And then this would be sort of your forecast. How many models are in failure moving forward? Now, regardless of which of these is the correct criteria, you can see that prior to this sort of second half of 2017, very few models are experiencing tensile failure. But going into 2017 and 2018, we would be seeing this acceleration of models experiencing tensile failure. The other very cool thing about these models is that we're able to take those stress and strain values and produce calculations of what the faults would be produced from these models. So what these are showing are the magma chamber, the depth and distance, and the colors now indicate what type of faulting would be occurring. And these colors then could be compared directly to focal mechanisms and the seismicity. So we'll get normal faults above the magma chamber and shear faults or reverse faults on the edges of the magma chamber. And we can compare it to what was actually observed at the volcano and see that it matches very, very well to what was observed, where we have these reverse faults and some normal faulting events at the edges of the caldera system. So ultimately, then in hindsight, we can sort of put together a picture of what happened. And what is most likely that has occurred is that there was this large earthquake that was triggered by this this culmination of all of the shear failure on the southern portion of the caldera. So what we're showing here is the stress change induced by this faulting event. The blue regions are regions that are clamping shut. So anything with a blue region, you would not expect to have a dike move through that region because the rocks have been clamped together due to the stress change in the system. And then anything that is orangey red, those would be regions where it's opening up, and that's where a dike could go. And so it's really interesting is that if you look at the magma chamber, you look at where we're seeing tensile failure. So this little gray area right here is tensile failure on the magma chamber. And then you look at where the system is unclamping, and this is the location of fissure number 1. And so basically this magma chamber is the white region here. Where we're seeing unclamping is at the edge of that. Fissure 1 is right here, and fissure 2 is down the flank on this side. So it's very nice to then see that by using this systematic approach with the physics-based modeling, we can actually then point to not only the timing of the eruption, but using the stress values, we can look at where magma is going to migrate in the system if it is to leave that magma chamber. So in conclusion, the ENKF approach is very powerful, and it actually did a very nice job of tracking the evolving magma system at Sierra Negra in near real time. The Moore-Coulomb failure did a really nice job of showing where faulting events and earthquakes would occur and matched really nicely to the focal mechanisms that were actually observed from the volcano. We think that the eruption was triggered by the magnitude 5.3 earthquake that allowed a faulting event then to unlock parts of the crust and allow magma to migrate. And I would say that knowledge of the previous eruption from 2005 played a really big role in how well we were able to produce this forecast, even if it was a very fortuitous sort of sheer dumb luck situation. Um, in the future, where we're going, well, we're doing a lot of work to understand the seismicity. This is work that is being conducted by our colleagues at Chinese University of Hong Kong, looking at how the seismicity changed along the caldera, through the eruption to better understand how stress was evolving as the eruption occurred. We're also looking at the details of the GPS data to try to understand how the dike initiated and propagated. This is from my student Lily Lucas. And we're really trying to hone in on that part of the situation where the magma chamber broke. What did that look like? How did the eruption actually occur? And then also, how do we translate all this cool science to other systems? I'm working with colleagues at GNS New Zealand. We're applying this technique to Wakari volcano to understand the White Island phreatic eruptions and how we might be able to forecast those types of events in the future. I'm also working with a group at University of Alaska Fairbanks to understand elution systems. And most recently, we've been funded by the National Science Foundation to work with colleagues in Italy to apply this technique to Campi Flegrei to better understand the acceleration and seismicity there and the potential hazards of the evolving magma system at Campi Flegrei. All right, I will stop there and I thank you very much and I look forward to your questions.
Great job. Oh, the translation from the data to the visuals just really did it for
Oh,
me.
thank you.
It was very easy to understand once I got the visual. The best part about hosting these events is I get to ask the first question. I was just wondering, you talked a lot about the instruments and even like the measurement error and the ensemble equation. I was just wondering how many instruments did you use that were actually deployed on the volcano, not like remote sensing?
So for our forecast, we didn't use any. We only used for remote sensing.
Wow.
And for the forecast, we only used INSAR data. And part of the reason for that was when I applied for the fellowship at the National Center for Supercomputing Application, one of the things I was wanting to do, oops, sorry, my computer wants to update. No, we're not updating right now. One of the things I wanted to do was look at how we could monitor volcanoes in remote settings. So we do have a lot of work in the Aleutians as well, where it's hard to deploy instrumentation. But now, at the end, I showed some of the work we're doing now on the seismicity and the dike propagation. In that case, we are actually using data. So right now we have about 10 GPS sensors that are on Sierra Negra that are continuously monitoring the volcano. So we're now going back and looking at the details with those data. But for the forecast, it was only INSAR, which is kind of, again, why we were like shocked it worked because we weren't expecting that at all.
Yeah, that is a shock. That's good to hear. I know this was in 2018, but are you continuously monitoring to this day? Okay,
Yes,
interesting.
yeah, and these instruments are publicly available. The data are published publicly, so you can look at the inflation, and it is currently inflating, and the current inflation has almost reached the magnitudes that it hit in 2018. So my colleagues are like, oh, this could be happening again soon. My funding has now ended for this particular system. We're tying up the loose ends of papers, but of course I'm always very interested in. I had some great conversations with the group at SOAS because Garrett Ito has been funded to do work in the Galapagos, and we're looking at ways to get back there to get more data, more information.
Oh, I'm excited to see what happens.
Yeah, me too.
I'll give other people a chance. We do have a question in the chat for Mary. Do you use drones to gather data?
Yes, and actually, my colleague Pete LaFemina has done a lot of work in the caldera to understand the lava flows and also the caldera structure because there was a lot of co-seismic displacement during the eruption. So the earthquake occurred and there was sort of a drop down in the caldera and then it reinflated. Sorry, my puppy is. I have an 18-month-old golden retriever who's very mad that she's not being allowed in here. She's letting me know. So yes, we do use drones to understand the lava flow structures, but then also to map the fault displacements, both prior to and during the eruption and after the eruption. Yes.
Perfect. Does anybody have any other questions? Feel free to unmute or put it in the chat.
So I will say one of the biggest things that we're working on now is trying to make this more accessible to monitoring agencies. One of the things that's sort of unsatisfying to me about the approach is by using commercial software, it's not something that everybody can use because the ComSol licenses themselves are something like $40,000 or $50,000 for non-academic use. So our colleagues at monitoring agencies around the world just aren't able to purchase those. So we are working really hard to come up with other approaches, and we do have like a Python analytical version that is open source, and we're working hard to create other open source approaches. So observing animal behavior, I don't actually know. So I have not talked to my colleagues about what the animals on the Galapagos Islands might be doing prior to the eruptions. I would think, though, because there is such an acceleration in seismicity, that it probably does impact wildlife quite a bit, especially when you start to get magnitude 4 and 5 earthquakes. So I'm sure there is some sort of response from the communities of animals living on the islands.
So I know you said you've used only kind of like remote sensing, no physical instruments on there. If you were to run this again, what would you have liked to have seen? Any kind of improvements if, funding wasn't an option or an issue, I should say.
So fortunately for Sierra Negra, we do have the continuous GPS stations, and we are going back through the data now. It's slower than we would like. One of the things that's tricky about continuous instrumentation is that, it's giving us information every second. So then you need to bin it into maybe daily bins. When I talked about the computational time to run a hindcast for only 2014 to 2018, just using INSAR data, and I think let me go back. I can't remember how many time steps. It was 67 time steps. That took weeks to run. So now if you add GPS data, and now maybe you have, so even if you're doing daily bins, that's 365 time steps per year. You're talking running over months and months to get it to work. So one of the things that we're trying to do is use machine learning and AI to speed up the process, so that these can be done more swiftly. The other thing that would be really cool that I would love is to have run the models to present and then just assimilate as every day comes in, right? So that if you're a monitoring agency and you have data rolling in, if you have this framework, just at the end of every day, you assimilate what came in that day and then provide the next day's forecast. So that would sort of be the goal, so that you're not trying to run a decade worth of information. You've already run it all and you're at present and you're assimilating and you kind of move forward. So that would be sort of my ideal.
I was
Like, so
just
then,
about
and
to
then,
ask how quick
yeah,
is the
and then if
turnover
you
in
say
data?
like we're having major errors in the models in these regions, then you can say, okay, we need another GPS station right there. Or maybe a seismometer would be really useful if we put it on this part of the volcano, because that's a part where our model is really struggling to resolve. Or there's a lot of error there. So I do think in the future, that's the type of thing we'll be able to do. We'll be able to say like, okay, we've assimilated to present, it's handed off to a monitoring agency, and they can sort of move it forward. The other really cool thing about this particular technique, the ENKF, is that you can swap in and out models without actually changing the math. So in this equation, we have this A matrix. I can take my model out and say, okay, we've updated the model sufficiently. We want to put a new model in, and you don't have to change any of the coding at all, which is really awesome, which I really appreciate about the technique. I see another question. Have you seen a connection with solar activity flares, geostorms? I haven't. There's there are a lot of different things that people have pointed to as potential triggers for volcanic eruptions, such as increased rainfall, or we in Alaska, we've looked at changes in glaciation, changes in ice levels on volcanic systems. And it is really tricky because, especially when you start to dig into this sort of stress state, I don't know if there's a good I don't know what is a good model, but I think the thing is that these volcanic systems, as they're expanding, stress is building up all around the crust. So sometimes that stress is at a near tipping point. So you could have something that could trigger the eruption that may seem uh, outwardly very small, but just enough to tip the scales. But it's because that stress has been built up over so much time. But it is difficult, especially when you have a magma chamber that's 4 kilometers deep, because you need it to be able to translate it to quite a depth to impact the system. So I'm not sure how, like, I don't think solar activity or flares would be able to penetrate the Earth's surface enough to do that. But it's a really interesting idea, and it's certainly stuff we think about. Can you say something about the roadway network and other infrastructure? Yes. So one of the issues, especially in the Galapagos, is that these volcanic systems do not have a lot of infrastructure or access to get to them. So for Sierra Negra, there is a road that goes up from Via Mill, but there aren't road access to any of the other volcanic systems. So that becomes really tricky, especially if you want to put in continuous monitoring stations such as seismic or GPS. For volcanoes like Wolf, not only is it remote and there's no road access, the caldera itself is really deep and really tricky to get into. So you're looking at helicopter support being one of the only ways to get instrumentation into these volcanoes. In terms of the seismicity, so far the seismicity has been fairly localized around the volcano, and the road only goes up to the flank, and then you have to hike into the caldera. So it's not like the earthquakes and faulting within the caldera are upsetting any infrastructure, because there just isn't any infrastructure to upset. But when these earthquakes get larger, you could imagine situations potentially impacting the flank. We haven't seen that yet at Sierra Negra, so potentially not a huge issue in this system. Now, of course, for other systems like Campe Flegrei or Kilauea, yes, it plays a huge role, especially when you have these large seismic events or intense acceleration and seismicity, and it does disrupt the infrastructure quite a bit.
Great. I have to say this was a fantastic presentation. I was really excited and just nerding out over all the data. Thank you
Thank you so
so
much.
much. Thank you for joining September's third Thursday. Our next third Thursday will be October 16th. And if you want to find out more about volcanoes, NDPTC does have volcanic crisis awareness as well as a slew of other courses you may attend. So once again, thank you, Trish, for
Thank you
coming.
so much for the invitation. I really, really appreciate it.
Of course. Enjoy the rest of your day, everybody. Thank you.
Thank you.
Thank you so much, everyone. Have a great day.